University of Cádiz, where he's also an associate professor. He has participated in many research projects, national, regional and European ones, and he has also led some of them. And he also has been general chair in one occasion of the Intelligent Environments Conference. And he's mainly interested on the application of the research of artificial intelligence in areas such as assisted living, smart learning, and also smart mobility, which is the main focus of his talk today.
Thank you very much, Rupert. Good afternoon, the audience. Thanks for attending. So today I'm trying to walk you through the results of our papers and projects in this area of this research line of smart mobility. So, by the way, disclaimer, by now I have guessed that that image has been generated, of course, by ChatGPT. I just gave it the title of the talk and some ideas about the content, and it generated this pretty image. Didn't do it badly. You can see some over there, also on the road. So okay, well, let's take a video of the smart mobility with different elements. Before starting my talk, I just want to introduce myself, as Lupe said, just one more thing. I started my research in something in the past that was multi-agent system, and now are very hot again, thanks to LMS, and also semantic web. And slowly I've been moving to the area, to the other side of the road, with machine learning and deep learning, and started doing course in human behavior analysis, especially in mobility analysis and learning analytics. But I think more important than that, the we that are after this project is not only me. Obviously, I have several collaborators. One of them, one of the foremost, I would say the only father of these ideas, is my dearest colleague and also friend, Fernando de Rosso. He's also from Spain. He's working in Cartagena, in a place, and his research interest is also human mobility. We met each other in 2018, and from then we have been working on this project of smart mobility with a, I would say, successful collaboration. And well, by the way, was my camera over there was today his birthday, so Fernando, so happy birthday to you. Because indeed he was planning to come here, but we have just started for one bus, so it was the lucky one. So some of the let's say middle siblings or relatives in these projects, all people, a lot of Spanish researchers from different universities, and also a French colleague that have been working with us in all these different areas. So now, time to get down to the nitty-gritty. This is the agenda. I'll try to, I think, I must confess, I think I'm very ambitious in all the things I want to tell you today, so probably at some point I will check the time. I will need to skip some of these points. Let's see how it goes. So first of all, what's about this idea of the smart mobility? Well, as you know, we are totally surrounded of sensors and devices. Most of them, or some of them, are getting powered, as you see there, like Bluetooth, RFID, Wi-Fi, GPS, and also there is also databases from the call data records that some company keeps, where they also have information about mobility. So they allow us to capture this movement of people in different scales, local scales, national scales, international scales, and also indoor or outdoor in different places. Okay? But, always a but here, the access is quite limited for secrecy and privacy reasons, and the data sets we have found from companies, they are costly to be paid for. Okay? So it's not the way we want to do science with this data. So the alternative is to go to the open data. Okay? And according to Europe, with this idea of as open as possible, as close as necessary for the data, we looked into the possibilities that we had at that time to look for open data models. And the good news is a lot of municipalities, a lot of governments are already opening this data, the access to the data. You can look for a lot of portals offering different open data in smart cities or different aspects. But, dramatic pause here again. But they also have some cost because the granularity, trust on this data, missing data you will find in these data sets. So different aspects make us to put an effort, in this case in the pre-processing of the data. We need to devote a lot of effort, a lot of time in the pre-processing of the data that we want to use for this task. Okay, so it's the idea that we had some time ago. Why not match this idea of the open data on mobility, and mix this with machine learning and deep learning models in order to offer the following application or services. Some of them you can see in the slide. Okay, we started with the idea of predicting the use land. I will in a moment what is this. Then also try to forecast well consumption, how is this related with mobility. Then something more extensive would be the predicted police flows in a country, monitor traffic incidents, and finally, our basis idea was to try to predict the new hit song in Spotify. Okay, that's what we did the next song that's going to be a blast in Spotify. We'll show you how it will be predicted. Okay, but before that, let's see the ingredients that we need for our models to work. The main ingredients that we need as open data. Obviously, we started with our own nation, with Spain, and I have to say that we were lucky at that time because our government started to open a lot of data sets about mobility. It started with the COVID-19 thing. The government decided to publish open data on the mobility of Spaniards, people moving around Spain, just before, during, and after the pandemic of COVID-19. So we have that first data set that contain, you see, the movement of people in different disciplines in a very fine-grained level from February 20 to December 21, just before the COVID and 1 year after the COVID. So the information that we get from this data set is that we have the hour, the day and the hour, and the area of the origin of the movement, the origin of where the people start moving, the destination, and we also have the type of trip these people is doing, with only three classes. We have home to work, work to home, or home to other, or work to other. The other will be different from the normal pattern that people use when they go to work and back. The data was extracted from the mobile phone carriers. I think this was from Orange, the Orange company. On the one below, and the one there was about Vodafone, and also they used our national mobile carrier in Spain is Movistar. So they used the three of them to get the data. After that, a little bit after that, they also published a previous data that they had with Orange, and this case more aggregated. In this case was movement from region to region, not from location, specific location to location, no, region to region. In Spain we have 40-something regions, 51 if you take into account the one in Africa. So they use that information to see how people move from region to region. More data. We can also go to the official traffic agency in Spain. It's called DGT, Dirección General de Tráfico is the name. It's the one that for Spaniards is the fiercest one because it's the one they go to tickets for the speed. So they also have this page where you can see all the incidents that are happening, the traffic incidents that are happening in Spain in real time. And again, you can download the information and you can manipulate them. More general open data sources for flights. You can look for open flights on web, and you can get information on flights, and also for any kind of transport, like transit feed. You can look for it, for example, trains. You can see for each train in a country when it departed and when it arrived. So you, for example, can see which country in Europe is the one with the most delayed trains. Spoiler, Spain. So no worries about this, that's for sure. Okay? So I get that advice here is if you find one of these data sets, just upload it, but from time to time they tend to disappear too. Well, I don't know if you have some experience too with this kind of data sets, open data set, particular to mobility. I did my homework before coming here, so I looked for the Greek, for the Greek base, for the Greek data sets. After 2 days, I realized my mistake. I should be from Germany. But anyways, I will fix this in a later part of my talk. Anyway, for this, it's true that there are several sources, but there is some bad news. And I saw both reading post from last year. It's the slow death of open data, particularly here in Greece. So it's worth reading after my talk, actually. So you can go to that link, and for that, I will share the slide after that. Okay, now start with our applications. We start with the idea of modeling this problem of human mobility as time series. How to deal with time series. Why time series? Because we thought that for us, the idea of mobility is like having several matrices from origin to destination. So there are people moving from one neighborhood, location, region to another, and vice versa with other regions. So the idea, more or less, try to analyze this kind of time series movement in different areas. So we see then well to look for the machine learning, deep learning model that could work with this kind of data. So our first approach, not really with time series, but sort of our first approach with open data was the idea of land use discovery. So if you're wondering about what is land use, is to try to infer what is the actual use of a district or a neighborhood in a specific moment of the weekday and in a specific time interval. Okay? Monday mornings, Sunday evenings, Saturday nights. Okay? So that's the idea of trying to infer that. So how we did that? Let me come over here. So we started using this idea of VGI, this volunteered geographical information. There was a movement at that moment that people shared voluntarily their location in a part of the city. So we have like two main kind of social networks to get this information. The first social network is the traditional online social network like Twitter, with billions of likes, or Facebook, where people post their comments in some part of the city, different part of the city, on what they are doing. Having breakfast, taking people to school, working, having a good time, whatever. Okay? So we gathered those posts. The second type of social network is one that was called local. The group of this kind of social network was called location-based social network. As for example, Foursquare, Flickr, and also I think Java. I don't know if they are still working, but at the moment they were. And in this kind of social network, somebody goes, makes a check-in saying, I'm in this bar, I am in this restaurant, and then he or she can make some comments about it. So again, we gather this kind of post to try to analyze which are the main places, what are the people are attending to the main places in these areas. So then we match that, we match the topics people are talking to with the videos that we discover in that places, in order to afterwards, if we move to another area different from the city or different area, where we do have the first kind of social network, the one with Twitter, but we don't have the second one, we don't have any information about location-based networks, like Twitter, etc. Then we try to infer, according to the topics, what are the actual use of the land. That's the idea that we're trying to do. So that was the process. We started in the top, the red part, you have the Twitter information, the blue ones is related to Flickr or the location-based networks. So we started by collecting the documents. We're using some kind of density-based algorithm. We make these clusters of there are some interest here and here in the city, and then we start the topics. The people are talking in there. And the same, using these clusters, we group the places people are visiting, and then try to extract which kind of venue, specific venue is in that place. With that, we use several multi-classifiers like random forest, or support vector machines, and then try to infer afterwards. When we give new topics to the model, infer the value or places people are. So I have a little example over here. This is the Twitter information with the name of the user, location, timestamp, some text that's already classified with topics, because the keywords of those topics over there. Then for the clusters, the second part of the clusters location base, we have the cluster, the top two places in that area, in the cluster. We make the match, and then we have ready for new inferences. Okay, so far so good. Some results. For this we use the island of Manhattan to see how it works, but you can see nothing over there. But we did a study in the working mornings, how it was used, the island at the moment, on working afternoons, and here we have weekends mornings, weekend afternoons. If we make two of them, so here we have, it was working afternoons. You see that most of the places are used for wine and food. So there is a restaurant that they are using as a restaurant areas in that part. Okay? And from here you have some shopping services, and this is for the working afternoons. If we go to the evenings, things change, and most part that was yellow first, in the previous slide, now they are green, and they are for accommodation. No surprise about this, okay, there should be something like that, but yes, when we were able to detect these kind of things. Okay? So far so good. But second application, now we started using the city of time series, and we want to apply the incoming home and outgoing home flows from the city of Madrid, from 3 neighborhoods of the city of Madrid, combining this information that we have from the open data mobility that I showed you before, with data from smart sensors. What are smart sensors? We work with these Spanish companies called Hidroconta, and they provide this kind of smart sensors that it was in 10 minutes, they make a read of the water consumption and send the information in cubic meters. So the idea was, okay, let's compare the information that we have in these neighborhoods according to the open mobility data. So how people is moving with the cars, with the vehicles, according to the open data, with the water that is being consumed in that area in the day. So we did a study with our statistics, and for the seasonal component, we discovered this behavior, but something also very sensible. And you have the cycle pattern of a day of the consumption of water here, and the number of trips, number of people leaving houses or moving in the houses with car in the graphic below. So you can see that at night there's a drop of the use of water. Then from 6 a.m. people start using water only for having shower, etc. Then we have a dramatic drop at the evening, and then we again sleep increase at the end of the day. And this dramatic drop of water matches with the momentum we have more flows of people moving from out or in the areas we have seen. So this again makes some kind of sense that for people are not at home, they are not using water, so there are more movements and the other way around. So with this, we applied, in this case, one of the models we thought that was good for the time was the gate recurring unit, this G cells. It's a kind of long-term memory network with less data that the scheme to work. And this is the results. This is the coefficient measuring the error that we have in prediction, the number of displacement, the number of trips in that area, only taking into account the flow, the movement of people. In the past, we have errors like this, when we had the water data, the error was decreased. So from the 3 hours to predict the movement of people between 3 and 6 hours ahead, it was more or less fine. When we could do predictions of that, improving the prediction with the water. And the other way around, if you want to predict the use of water with the flow, you can also predict in the next 3 to 6 hours which is going to be the use of the consumption of water thanks to the flow. Third and last work in this area, when we move to the national level. So we try to predict the flows of people at the national level, as we have the data from the government. So this is a map of Spain represented, according to the Spanish Ministry of Transport and Mobility, the number of outgoing trips during the after the COVID period. You can see that the darker blue, you have the area, the more trips, the more movement of people is being in that area. But we need to enlarge that open data mobility with more data to calculate our predictions, and in this case, we use again Twitter as a external or complementary data source to improve the accuracy of our prediction. Why Twitter? With Twitter, we were able to know when people we think is traveling, because if we see that someone posts a tweet here, and before that 24 hours, he posts another tweet here, we more or less can say that, okay, this people is traveling. We don't know the reason, but they are traveling. And so we set some restrictions, we set some parameters to save or safely when someone is traveling according to the activity in Twitter. We didn't invent this, and we didn't make up this. It was already known in the literature. We just adjusted our models to the geography of Spain. So the results, including this part, we have again tried several machine learning models and deep learning models, the multi-layer perceptron over there, long short-term memory, and as bar max statistic element in the last one. So in the design of the slide, you have the prediction. This was just after the lockdown in Spain was released. So you can see that this was an increment of people traveling when we were again free to travel in our country. In this side of the slide, you just only see the prediction taking into account only the data from our ministry, the data from the open data mobility data set that our ministry published. And here you have the combination of that data from open mobility with the data from Twitter. And again, well, just to say that LSTM didn't perform quite well, but for example, for the case of Barmax, in some cases we performed quite well. And it was because of the amount of data that we had wasn't enough for these two elements, for the two models, but was okay for this one. Nice. Okay. Almost in the middle, so I think I have time for everything. Okay, next step, we use more complex models to try to keep working with the idea of humility, and now we move to a different kind of deep learning model that was starting to use at that time. That was called graph neural network. Neural network, but based on graphs. So the idea is, okay, we have seen that we have a map in Spain with different areas, different locations, and they are connected. Like I say, we have a new area, we keep creating a graph. So the idea is, okay, let's use then this idea of graph neural networks to try to capture the idea being the nodes, the districts, the regions, the towns of our country, and the edges, how they are connected, giving several kind of weights depending on which kind of information we want to measure between the exchange of flows of mobility in these areas. So far, the application we have done with this is for tourism prediction. So we divided our map in touristic areas within Spain, according to the census of our country, and combining again the open data mobility dataset, and now with Twitter, weather, and touristic infrastructure, with all this information mixed all together, try to predict in a qualitative way the income of tourists in a region. The qualitative measure could be a low income in terms of tourists, medium or high. Okay? We made some intervals, try to inferring if from this region to this region there's going to be in the next days a low, medium or a high level of movement of tourists. So this is our model, this graph neural network model. We feed it with different, from previous hours, with different data we have from the real flows of people that we consider as tourists in the data, and the nodes are representing the cities, and the edge are representing the flow between them. And to give weight to this edge, to see, is this edge more important than this edge between these cities? We use the gravity model that basically is going to say, okay, the importance of this edge is going to be calculated by the population of the city A plus multiplied times the population of city B, and it divided by the distance in kilometers of these two towns. Okay. With that, we have the basic gravity model with this, and now we can put more information in this edge. Which further information we try to put in this edge? First, weather. For the weather which we use, weather extracted from the airports. There's another open data page from airports. You see these red dots are the location of the airports. So spotted here, it didn't work. Okay, the weather didn't give it any extra information. So our hypothesis here is Spaniards are willing to travel in regards of the weather. Snow, rain, hurricanes, whatever, they're going to travel. Because the weather didn't add any improvement to the model. And then we also use the touristic accommodation. We thought if a place has a lot of hotels, a lot of touristic houses, probably people is more willing to move there if they are going to find accommodation that places with very small infrastructure in touristic houses or touristic accommodation. So you have a distribution. The yellow, if you see yellow colors, is where most of these elements are concentrated. So, for example, for tourist houses, they are concentrated on the coast, are concentrated in the island of Spain. Okay, all the coast you see yellow things. For the hotels, it's more spread. There's hotels almost in every, say, regions of Spain. And for camping and campsites, we have one part here in the inner part of Spain, and the Pyrenees is also a more dense distribution of campings. With that, we have this our prediction, and the yellow areas are good predictions for low income of tourists, medium and high. As you can see, more or less, we were able to capture the movement of tourists in almost all Spain, except for the north. If you see the northwest, for us was almost impossible to understand what happened there with the tourism. And also for the island. In the island it was also very difficult to get the real behavior of the tourism. We cannot predict the level, low, medium, or high tourist they are going to go there. Okay. So we also have, well, in this case, I wasn't involved in this one, in this project. It was moved out at first, but then I needed to leave. Now we are going to see different ways to also deal with human mobility, but in this time, in real time. Okay? The ones we have seen before is for prediction, but now we want to do it in real time, to see several things in real time. So, for example, apart from for real-time, should we still use machine learning models, or there are other alternatives. For example, a rule-based model. Probably you are quite aware of the CEP, or the set processing, or complex array processing that is set to use this. So we, in this project, my colleagues, Fernando, in this project, they rely on a different approach. Very quickly, the idea of SIP is that we have a stream of events, and these events are going to go through some agents with some event condition action rules. They detect the events and create a new simple or complex event that will move to another event until we have the final situation that we have inferred from there. So these people, they use it for determining the trajectory of vessels in the sea. So they have the vessels sending signals about their location. They make some kind of filtering of these points they had, and then with different rules, they were able to first establish what are the real positions, then their movements when they were moving towards different east, west, south, or north positions, and finally a complete trajectory. And apart from that, they also were able to study the relationship between vessels, not only the one vessel, but also between vessels. So they got data from, again, data from trajectory from vessels, from 3Ds, and they were able to do things like this. They did things like this. They tried to first detect illegal behaviors in fishing. So here you have the normal behaviors for a vessel of a boat when they are doing the fishing tasks. So it's something like that, zigzag like this. But when you see a vessel is doing things like this, it's perhaps it is not allowed to be in this area, and then moving quite quickly in different areas trying to fish. So this is an idea to identify illegal fish behaviors. Another application was about the smuggling behaviors. Remember I told you that they were not only able to identify the trajectory of one vessel, but the relationship between vessels, and some kind of smuggling behavior could be two boats, the vessels that are approaching, they exchange something, and they separate. Yes, and again, they were, so the blue and the red are these two vessels, and it was identified using this set procedure. Okay, two more, I'm there. So the next one, we again move to the use of machine learning, but now instead of using texts, instead of using open data mobility, we use images. In this case, traffic images from the official agency of traffic in Spain, the DGT. Let me show you an example. If I'm able to change my screen, right here. Okay. Okay. If I show you this is I show you in the presentation. I will work in a moment. So we have images like this. So you, the DGT offers you an API, or not an API and a URL, but you can access the URL and then you get real-time traffic images like these ones. So you have the stamps below the DGT and the timestamp of real time. So we were able to have a script to collect images in 1 week in order to see if our models were able to detect several incidents that we were interested in our logs. So let me go back. So the idea was to detect this kind of traffic injections, but now using this idea of the cameras. And you can say, okay, but you have Google Maps, and there are ways, and they work perfectly to warn you about some kind of traffic injection ahead. That's true, but we try to avoid any kind of third-party data, to use the data that the road operators they own by themselves, instead of relying on others' partners. So our thought was, let's try to use our own resources to detect this kind of broad traffic patterns. So again, as I told you before, we went to the DGT and to capture all the images it was 1 week or 2 weeks, capturing just these images. So our idea or proposal was to try to determine these 4 events. Just a normal situation with a free traffic situation, traffic jam, an accident, and some kind of more important point of fire in the road. Why these 4? This 4 was because we were using traffic net dataset for training our elements, our models, and this traffic net, if you take a look at this dataset, public dataset, offers these 4 categories. It's the categories we were trying to use. Okay, that was our aim, and this was our architecture, our proposal. So we have a crawler that was continuously reading the information from more than 1,500 cameras that were already set in Spain with this information. Every 4 minutes, we were collecting these images for training, and then in real time, when the model are trained, in real time, give the monitor with the real simulation according to the images. For that, we compare 3 models, 3 models that works well in deep learning area with images, was convolutional neural network, CNN, BG16, and Obsession. These 2 were taken from itself, just as they were, and we prepare one and adjust it as the senior. So that was the data set that we used, the traffic net for training, and then the DGT data set, we used some part from training and some part from the test, as you can see. The problem here, just to let you know, we had a problem at that time that we only had, at the moment, traffic, was only for people in the roads. We only had images with dense traffic and free traffic. No accidents, no fire. That's for good for people, bad for us, for the test, but anyway, we can do something with this. The problem is that if you see the images in traffic net, the images in traffic net are as clean as this. Easy for a machine to know what is happening there once it's trained. But the real life is not that so. And these are the real images from the DGT. You can see that we have some kind of fog, we can have the sun just part of the images, or we have very blurry images. So how this model are going to cope with this kind of images? Provided that we are going to train them also with this kind of images, we expect to improve the results. Okay, these are the 3 models that we're using. I don't know in technical details, but just to know that we adjust, tune the CNN model, and then we take from the site, we take the 16 and the section model. Both are known to work well with images. We define the metrics, the most important of it, the difference score and the accuracy, and these are the results of the models just for the traffic net, without any DGT images so far. So you can see the accuracy of these 2 of the self-elements models were quite good for, let's say, already cooked images, not so good for our own senior. Okay? But now, we introduce the DGT images, and then we have, let's say, something that surprised us in the results. As you can see, the 2 of the self models were quite good in detecting when there's fluid traffic, and also they were for dense traffic. But ours was more able to detect traffic jams than the other 2. Okay? So this is the thing with the black box. We didn't know about this. Okay, we didn't know the reason about this, but it seems that not very big difference. But it's true that our CNN was more accurate when trying to detect dense problems. Limitations. What we found when we look into some specific images. So you see the first image of a tire, you will see these are dense, you will see this fluid, and the SS, well, it is fine. Okay, according to our machine, it was fine. probably because of the lights. And the second one, fluid, dense, the traffic jam, the accident. Well, again, it's dense, but it's fluid, but it was classified as dense due to us parked cars. Okay, so still needs some improvements in there. Regarding to the ongoing work, I will go to the last part here. Now we're still working in this area, and now we are working with this idea in trying to improve our results with this kind of network, YOLO. Because YOLO are able to, let me show you in a picture. YOLO is unable to detect which kind of vehicle you are talking about. It's a truck, it's a car, it's a motorcycle, it's a bus. So it gives you more information about this. It would be useful at some stages. And we are mixing this information with weather and air pollution data. Our new goal is to try to predict the pollution in a city. So our first preliminary results, not yet published. We have done some testing in Madrid and Bilbao. We take the idea of, okay, let's take the images. Let's still work with images. We have a triangle, this the dots, the vertex of the triangles are cameras in the city. One camera, and 8 pollution stations. One pollution station, and another one. And let's take all the cameras inside, within that triangle. So let's analyze the images in here. Let's see according to the images, which is the pollution that we think according to the type of cars that are moving around that area, and let's check with the air pollution station. If this is the signal. If we can infer the pollution from the images and check it with the air pollution system. Why? Because if we move to another city with cameras but with no pollution station, we can try and now, just from the images, try to guess, to infer what is going to be the air pollution in that areas. Okay, let's work. The one that we went crazy and said, we have applied all of this, our knowledge, to the physical world. Let's move to the digital world. See if flows of things in the digital world can also be predicted by our algorithm we have used before. So again, this is not our special idea. This has been done before. Probably you know about PageRank only from Google. Sort of. It's the idea of how people is moving in the digital world. And apart from that, before us, some other people have done this in games as World of Warcraft, and other simulation life groups. So this is what I fixed the German audience. Okay, so we try to see the next hit in Spotify. So these are my favorite groups really great groups in German, especially from Montreal. So the idea was, okay, are we able to predict the next how songs are going to move around the whole world, and then when we have this musical, let's say musical mobility path, to predict when a song is first streamed, let's say Australia, which one is going to be the next country which this song is going to be streamed just after Australia, and then the third country and stuff. So that was our idea, and I'll show you the results. So basically, we went to Spotify, we get the data from the Spotify API, they publish the top 200 songs in each country every day. We collected that for 4 years. Then we did some data cleaning. We removed from the list all the well-known hits. So nothing about Britney Spears, nothing about Muse, nothing about real groups because they distorted our data. Then we analyzed if these are the countries, how the songs, as something move around the countries. Finally, we try to go with the path, music mobility path, that the songs go from one country to another country. That was more or less the idea for doing that. Again, for doing that, we use a graph neural network. This is the countries that we were able to look into, because this work also has limitations. As you may know, in some countries, especially in Asia, Spotify is not permitted or it's not working. So we don't have a real, one of the big points of this course is to have a real picture of the entire world. We look for songs as a guest. We remove all the mainstream songs, and we look for songs showing this behavior, like the snowball. So a song that starts little by little being played in different countries, and from at one point it gets some kind of success. Being a not very well known song has some kind of success because this kind of snowball behavior. So we went for that songs, trying to use as a training data for our system. This graph you see here is the idea of from one country to another country, how the songs are moving. So the wider is this line, the more influential country with the one who's going to the western. So we have Germany, I think over there, and they go to Luxembourg, I think it is. So the people from Germany have some kind of influence in Luxembourg. We have covered the path of songs from 3, 4, and 5 countries. I mean, starting from one country and reach the third country, 4 and 5. And this is the number of songs that traverse, that follow that path we see there. Mostly, I mean, making a summary, we see that there was some kind of pattern that songs go from the north of Europe to the south of Europe, from the west of Europe to the east of Europe, from the east of Europe to the west of Europe, but never from us, Spaniards, Italians, Greek, from south to north. We didn't see that behavior in the songs. No. But we had an influence in South America. Okay, last thing, we take a specific song, Toxic, not from Britney Spears, sorry, Toxic, from this Boy With You, I think it's from Australia. This is the path that this song was moving around, okay, with different branches. This was the real country from this one, from these two, the real country, the actual country, this song moved after the lesson here, and this was the one we predicted this song was going to move, would be streamed next time. So we had some hits here, and also with Germany here, with Estonia, with Ecuador, and with Peru. So we were able to anticipate what will be the next country the song will be streamed according to the path. So, finally, my conclusions. It's true that after the pandemics, we have seen a lot of new movements about the open data regarding to mobility, so I think it's a good moment, it's a momentum to take this data and do some analysis with it. Probably the idea is to mix, the success for this could be mix different kind of sources of data, not only the mobility, weather, as we see, also anything you can pick out of this kind of new data sources. And then, well, we have been using this machine learning and deep learning models. We see at the moment that it's easy to implement, and they were quite well adjusted to the problem that we have. So for the future, again, try to, as I said before, integrate new data sources and make this more accessible to the citizens, create dashboard integrated with digital twins. And of course, as you know, working, I had the paper in my laptop anyway, you can go there. As crazy as it may seem, you can ask LLMs, where should I move next? And ChatGPT is going to answer, you need to move next to this country, to this country, according to your information. There are 2 papers just published in archives last year and this year, talking about how these mobility problems can be also solved directly by LLMs. So, most of the papers we have been talking about up there, just you need to find them or you ask about this, just drop me a line. And my colleague Fernando is maintaining the repository. Most of the code we have seen, or the application we have done, is published and maintained for us in the GitHub repository. So thank you very much. I hope you enjoy it. So my
songs, for example, because what you call propagation somehow is just the timing when they appear. Can you go deeper than that?
Yes, sure. Yes, I'll give you later, but yes, first, from our side, we decided that there were two important parameters in the songs to know when they're going to move. We got when they appear in that country, since the song started, and how long it was kept in that country in the top list. But it wasn't enough. So one of the reviewers asked the same question as you, and he, or she, we don't know the reviewer who was, told us to look into the migratory flows. See, the information about migration has something to do with the cultural movement of the songs.
What about some obvious things like beats per minute or something like this? You're not looking into
What? What's up with it? No, never look at that.
Come on, this is music.
Yeah. We started. We keep working on the music line for different things. What we did, instead of looking to the, let's say, physical raw data of the songs, we looked at the some features of Spotify offers our song that are danceability, how danceable it is, balance, if it is positive or not, and energy. So we did some improvement to this thing with other works, looking at that, but never to the physical thing. But okay, thanks for selection. Questions? It's been so clear. Okay.